Namaste. Welcome to the next video of Machine Learning Practice course. In this week, we are studying end-to-end machine learning project and we are discussing various steps that are involved in end-to-end machine learning project. So far, we looked at the first three steps. The first one being looking at the big picture, second is getting the data, and the third is data visualization. Now we are on the fourth step, which is about preparation of data for machine learning algorithm. So in this video, we'll look at various steps that are involved in data preparation for machine learning algorithm. We often need to pre-process the data before using it for model building due to a variety of reasons. There could be errors in data capture. Data may contain outliers or missing values. Imagine there is a sensor measuring the wine quality, and if sensor starts malfunctioning, we might see different values than otherwise. In machine learning algorithm, generally we use different features to represent an example. These different features may be at different scales. The current data distribution is exactly not amenable to learning. So we apply certain steps for data pre-processing, and these steps are like separating features and labels, handling missing values and outliers, feature scaling to bring all features on the same scale, and then applying certain transformations like log, square root on the features. So you can see that these four steps that we are talking about are addressing the issues that we discussed a few minutes ago. For example, handling missing values and outliers help us to fix error due to data capture. If there are outliers or missing values in the data, the handling of missing values will take care of filling missing values with suitable values. The feature scaling helps us to bring all features on the same scale, and transformations like log and square root might help us to get the data distribution that is more amenable to learning. It is a good practice to make a copy of the data and apply preprocessing on that copy. This ensures that if something goes wrong, our original copy of the data remains intact. Let's look at the first step, where we separate features and labels from the training set. So in order to separate the feature, we simply apply drop method on the training set. So in this case, we dropped this label, which is quality. Before applying data cleaning, we first check if there are any missing values in the feature set. One way of finding it out is as follows. So we do column-wise operation. We calculate, we apply is_na function on each column and then sum it up. This counts the number of nans in each column, or number of missing values in each columns. In this dataset, you can see that there are no missing values because the values in the column are the values that we obtained after this operation are all 0. So there are no missing values. In case we have non-zero numbers in any column, we have problem of missing values. These values are missing due to errors in recording, or these values simply do not exist. If the values are not recorded, we can use imputation technique to fill up the missing values. The second option is to drop the rows containing the missing values. If the values do not exist, it is better to keep them as NaN. sklearn provides a couple of methods for dropping rows containing missing values. We can call drop_na method or drop method to drop rows containing the missing values. But what happens is, in case of machine learning, the data is scarce and throwing away any data like this could be costly. Hence, we try to use imputation technique to fill up the missing values. sklearn provides simple imputer class for filling up missing values. And these missing values can be filled up with, let's say, median value or average value or maybe lowest value or highest value, I mean, depending on the feature and the context. In this case, we import the simple imputer class from sklearn and we apply the median strategy for filling up the missing values. In this case, every missing value will be replaced by the median of that particular feature. We first call the fit method on imputer for that particular feature. The fit method learns the strategy. It will basically calculate the median value in this particular case. We can learn the statistics learned by imputer with simple statistics underscore member variable. And here you can see median values for each feature in our dataset. We can cross-check it by actually calculating median on the feature set. And you can see that these values match exactly. This is 7.9 for fixed acidity. The imputer also learned 7.9 as the value of median. Then 0.52 for volatile acidity and so on. You can check each of these values over here and the values that are learned by imputer, and we find that these values are matching. And note that we have already separated the label, which is quality, which is not present in the feature set. Finally, we use the train imputer to transform the training set such that the missing values are replaced by the medians. We simply call the transform method on imputer. The transform method returns a NumPy array and we can convert it into data frame if needed. We can look at the shape of the transform feature set, and you can see that it has got 1279 examples with 11 features. We can convert this NumPy array into the data frame. Sometimes we might have text or categorical features in the dataset, and we need special handling for these features. Since machine learning algorithms prefer numerical data, what we basically do here is we take these text or categorical attributes and convert them into numbers. Let's look at how to do it. First option is to convert the categories to numbers. We can simply use ordinal encoder transformation for that. Ordinal encoder transformation called the fit transform method on ordinal encoder objects to convert text to numbers. And text is also an example of a category. The list of categories can be obtained via categories underscore instance variable. One issue with this representation is that ML algorithm would assume that the two nearby values are closer than the distinct ones. That could be a real problem if there is no systematic ordering in the categories. In that case, we use one-hot encoding as an option. Here, we create one binary feature per category. The feature value is 1 when the category is present, otherwise it is 0. Only one feature is 1, which is hot, and the rest of them are 0, which is cold. The new features are referred to as dummy features. sklearn provides one-hot encoder class to convert the categorical values into one-hot vectors. And again, one-hot encoder is a transformation so that it has got fit underscore transform method. It returns SciPy sparse matrix as an output rather than NumPy array. Because the, the, the new representation is pretty sparse, many features are actually 0 and only few features are 1. So this enables us to save a huge amount of space for this new representation. In case you want to convert it into dense representation, we can do it with two-array method. Again, the list of categories can be obtained via categories underscore member variable. As we observed that when the number of categories are very large, the one-hot encoding would result in a very large number of features. This can be addressed with one of the following approaches. We can either replace one-hot encoding representation with the categorical numerical features, or we can convert it into a lower dimensional learnable vector called embeddings. So it is often observed that different features that are used for representing examples are at different scales, and most of the machine learning algorithms do not perform well when input features are on different scales. Scaling of target label is generally not required. We generally do scaling only on the features. There are a variety of scaling approaches that can be used. The first one is min-max scaling or normalization. In min-max scaling, we subtract minimum value of the feature from the current value and then divide it by the difference between the minimum and maximum value of that feature. The values are shifted and scaled so that they range between 0 and 1. A scaler provides min-max scalar transformer for this. One can specify the hyperparameter of feature range to specify the range of the feature. The second approach for feature scaling is standardization. In standardization, we subtract mean value of each feature from the current value and then divide it by the standard deviation so that the resulting feature has a unit variance. While normalization bounds values between 0 and 1, standardization does not bound values to a specific range. Standardization is less affected by outliers compared to normalization. A scaler provides standard scalar transformation for feature standardization. Note that all these transformers are learnt on the training set and then applied on the training and test set to transform them. Remember that we should apply the same kind of transformation to training and test in order to have the correct machine learning pipeline. This makes sure that we are applying the same kind of transformation on the test as that was applied on the training set. We never learn these transformers on the full data set. So depending on the nature of the feature set, you can decide your transformation. So for example, if your data set has outliers, then standardization might be the transformation that you want to use rather than normalization. So in order to make sure that we apply uniform preprocessing to both training and test set, we use a pipeline class provided by scikit-learn. Pipeline class helps us to line up transformation in an intended order. Here is an example of pipeline. The pipeline class, we specify a sequence of transformation. Here we have two transformations. One is the imputer transformation and second is standard scalar transformation. So the imputer transformation helps us to fill up the missing values, whereas standard scalar helps us in standardization. You can note that each step is defined by the name and the estimator pair. For imputer, we are going to use simple imputer estimator, and for standard scalar, we are going to use standard scalar estimator. Each name should be unique and should not contain double underscore. The output of one step, in this case of the simple imputer, is passed to the standard scalar. So what really happens is, whatever data that we get, we first fill up the missing values with simple imputer, and then we apply standard scaling on the resulting data set from the simple imputer. Now, in this transform underscore pipeline, the standard scalar is the last transformation that we are using. So the pipeline would expose the method of the last estimator. In this case, the last estimator is standard scalar, and since it is a transformer, we call a fit transform method on the pipeline object. So this works well when we have features of the same type. What if we have features of different types, and it is very common in real world situation that features will be of different types. Some features will be numerical features, some features might be categorical features, and so on. So transforming this mixed feature can be a challenging thing. But sklearn has a way of sklearn has provided a way for us to transform these mixed features. sklearn provides column transformer for exactly this particular purpose. We can import column transformer class from sklearn.compose package. In our current data set for wine quality prediction, we do not have features of mixed types, or all features are numeric. So it was easier for us to apply, the same kind of transformer on all features. So here, for the purpose of illustration, we have a code snippet using the column transformer. Here we are defining what kind of transformers that should be applied on different type of attributes. For numerical features, we'll use num underscore pipeline, and for categorical features, we will use one-hot encoders. The column transformer applies each transformation to the appropriate column and then concatenates the output along the columns. And the columns are specified over here. Here we have specified numerical attributes that are coming from this particular list of wine features. So this is a list of attributes on which this num pipeline transformation will be applied. You have a categorical attribute which is place of manufacturing, and this one-hot encoder will be applied on this place of manufacturing, which is in the list of categorical attribute. Here there is a single categorical attribute, but if we can also specify multiple categorical attributes if they exist in our data set. So this is a very useful transformer to learn, and this will be very useful in real life situations. However, there is one restriction. All transformers must return the same number of rows. If that does not happen, we'll have problem while concatenating the outputs along different columns. In this case, the numerical transformer returns a dense matrix, while the categorical transformer returns a sparse matrix. The column transformer automatically determines the type of the output based on the density of the resulting matrix. That's all from the data preprocessing steps. We looked at how to handle the missing values, how to standardize the features, and how to apply the preprocessing uniformly to training and test set using pipeline class. This content will be very useful for you while solving the real-world problem. In the next step, we will look at how to train the machine learning model.